Okay, hello everyone. We are doing a little introduction to parametric equations. I think parametric equations are a really clever idea. It's so simple, so powerful. What we're going to do is we're going to model, in this case, I'm going to do an example of projectile motion in which we break down the vertical and the horizontal components and we describe each of them with a third variable. In this case, with projectile motion, it makes total sense to use time, all right? So we can write the vertical component and the horizontal component both in terms of the time over which the particle is traveling. All right, so if we are launching something, here we go. We're just going to shoot something, and it's going to be at some angle theta. And so if we just break down that vector into the horizontal component and the vertical component and describe those based on our rules of physics, we can model that behavior. So here's an example from my youth. I've got parents that live with a nice little barn out back, and there's the garage, that's the garage, and then there's a chicken coop with a door. And when I was a kid, we used to mount rubber bands on either side of this door, open up the door, stretch the rubber bands back with a Hylex bottle handle, load a water balloon, and launch a water balloon out of that room. It was a lot of fun. You stretch it way back and shoot it, and you can go pretty fast and pretty far. And so I've modeled that projectile being launched at about 15 degrees. And I'm estimating, based on previous experience, that it's traveling at about 20 meters per second. Okay, so to break that down then, the horizontal component, you know that's going to be the cosine of that angle. So 20 meters per second is the initial velocity of that particle, that water balloon traveling in that direction. It's going to be 20 times 15, cosine of 15 degrees. We're just going to neglect wind resistance and all that. And that's about 19.3 meters per second in a horizontal direction. Now, vertically is a little bit more complicated. I'm estimating that the height of the launch of that water balloon is about 4.3 meters off the ground. And the vertical component then will be the sine of 15 degrees times 20. And that's how much it's traveling upwards. But gravity is pulling it back down at a rate of 1/2 at squared, or in this case 4.9 t squared, gravity being 9.8. So simplified it here, and that's the vertical component. All right, so I put that into my calculator and turn it on and go to y equals, and that's the next problem, going down here to this one. And I put it in, I'm in radian mode, so I put in pi over 12 for 15 degrees times 20 times t, and here it is 4.3 sine of pi over 12 times 20 times t, and 4.9 t squared. In parametric mode, I've got a window here that is the clock on this water balloon is going to go for 1.8 seconds. I know from experience it doesn't go much longer than that. I'm making it a small step, so it's a 20th of a second. I'm starting just in my window. I want to see back into the garage, and forward about 40 meters is maybe about how far it's going to go. And then there's the graph. Okay, so this is the way parametric works. When I go to trace, I see three things: the time, and then the x and the y. All right, so I can trace along here. If I go back to if I hit trace and then go to 0, it'll start at 0. And then I can trace forward. So this is kind of like time lapse. There's the water balloon traveling. How far does it go? My driveway was set back about 50 yards, so I don't think it quite makes it, but there it is, around 31 yards, something like that, 30 yards. I could find out how high and do other things like that, but let's do it mathematically. So parametric, you guys should be able to do some basic things like the following. You should be able to graph like we just did by hand if you go slowly, but calculator's faster, but then also eliminate the parameter. What that means is we're going to solve and express, in this case, usually we're going to do y as a function of x. So what I want to do is get t, solve for t. So in this case, if this equals my x variable, all I need to do is say that t then is equal to x over 19.3. And then I take that and I sub it into my y equation. So I can have y of x then is going to be 4.3 plus 20 times the sine of 15 degrees, and then times now t, which is x over 19.3, and then minus 4.9 x over 19.3 squared, okay? So that would be solving and eliminating the parameter. I did, just to show you, I did put this in advance. If I change the mode and go down here and change it out of parametric mode, I didn't really show you that that's how you go into parametric mode. I'm coming out of parametric mode, go to y equals. I've typed this in its solve form. I simplified a decimal or two there, but if you go to the graph now, I've kept the same window and you'll see it is the identical curve. It just doesn't show the same window for the time. It goes before I launch it and well after, but the curve is the same, okay? So you should be able to find the derivative of this function. Well, when we find the derivative, normally it's dy dx, but in this case, it's going to be dy dt over dx dt. Okay, so remember this, commit this to good memory. That's two fractions, each the derivative. So the derivative of y is going to be, in this case, the decimal here is approximately, I think, about 5.2 when I do this math right here. So it's going to be 5.2, then minus 2 times 4.9 is 9.8 t over then, well, the derivative of this is just 19.3 t, or 19.3. So that's the derivative. If we wanted to find the tangent, the equation of the tangent line at t equals 1, we'll say, I would just simply put in 1 there and do the subtraction. I would get what the slope m would be then, or the derivative there is negative 4.6 over 19.3, and then I could just put that into point slope form. When I'm at t equals 1, I'm at 19.3 for x, and I could just put that in, evaluate it for y, and then put that into point slope form. And that's the easy way to go. And you can just keep it in its ugly decimal fractions. You do not need to simplify it, especially, obviously, if this is in a no calculator portion of the AP exam. Okay, when we're finding the second derivative, this is a little bit more tricky. What this is really saying is we're going to take the derivative of this function here for the first derivative and then take it a second time with respect to my dx dt. So I'm going to repeat that denominator. So if I divide this in, that's just going to be a constant. And then when I divide this in and take the derivative, this will then be minus 9.8 over 19.3, because this fraction here, when I take the derivative, will just drop the t, and then that's all over 19.3. So this would equal negative 9.8 over 19.3 squared. Again, won't put that on the calculator. You can if you want. Find the points of horizontal and vertical tangency. Well, in this case, we've seen the parabolic trajectory. We know that there will not be a vertical point of tangency, but the horizontal point of tangency will just be, when is this derivative going to be 0? And I could solve for that. That would be that horizontal point of tangency. And then finding the arc length, we are going to do that on the next problem, but on to our next example. There we have it, famous play from NFL history. Okay, very memorable moment, was it not? And I am attempting to model it here with parametric equations. I studied the film, I kind of put down a coordinate system, I worked out the math, and we've got the football. That's being snapped back to Russell Wilson, being modeled by this quadratic for the x. It's coming back and then changing direction going forward. A little bit unrealistic because the football's sort of accelerating, wouldn't really happen, but oh well. And then here's the y component. These are just linear and relatively accurate. They do converge all spectacularly to that one point where the interception is made. I've typed it into the calculator. Here it is. The cool thing is with the trace feature, you can play it out. I'm just advancing 1/10 of a second at a time. You see the ball going back. Russell Wilson's thinking about what to do. He throws it. Here's the football moving. I can jump to the receiver here, and you can see moving towards the ball. And then there is Malcolm Butler a little bit ahead of him, also going towards where the ball will be. And Here's the football coming in, there's the interception, all right? We can zoom on that if we have time, but moving on to the math, I want to show you guys how to decide if there will be a vertical or horizontal point of tangency. We can see here, we would anticipate that there will be a vertical point of tangency. That will happen when we take the derivative. dy dx in parametric is going to be dy dt over dx dt. Be careful to avoid making the mistake that we tend to put things x and y, and we have coordinates or vectors, and you tend to want to put the first thing on top. So always remember it's the dy that goes on top over the dx. When I go back to my equation here, take dy, that's going to be negative 0.76. Then the dx, the 2 comes out, makes that 2.2. T drops out. I get the denominator. When will this be 0 in the numerator? The answer is never, so there's no horizontal tangent, but there is a vertical tangent point when t is 1.5. I just solve that, set that equal to 0, divide 3.3 by 2.2, and I get 1.5 seconds. Finding the second derivative, again, this is just a formula you should know. You're taking the derivative of this with respect to t and then dividing it again by dx dt. So very carefully, what is the derivative of the top with respect to t? Well, it's going to be the bottom times the derivative of the top, which is 0, minus the top, which is negative. So it's going to be a positive top times the derivative of the bottom. So it's going to be 0.76 times 2.2 when I take the derivative of the bottom, and then that's over the denominator squared, 2.2 t minus 3.3 squared, and then when I take, that is the denominator of my original fraction, and I add that in again, and that's a multiplier, so it's to the third, to the second, and then when I divide it again, it brings it to the third. And that would be the equation for the second derivative. Okay, how far does the football travel? Well, we're going from t equals 0 to t equals 4.3 seconds is how long that play is. This is the formula for arc length in parametric. You're just taking the derivative of each component, and when you get the derivative, you square that, and we then integrate the square root of that. It's just the Pythagorean theorem, very simple. So here I've got it figured out. Now this one is one that I will definitely do in my calculator. So if I just go to my mode and change that to function mode, I've already typed that exact expression in. There it is in my function mode. When I go to the graph, it conveniently shows up on this graph, and then I can have the calculator do the integration. So I just do second trace, hit number 7. I'm going to start at 0 and then go to 4.3, and there is the integration, and lo and behold, that football travels about 11.88 meters. 11.88 meters, and that makes sense if you go back to the original graph, that it was out here on about the 6-yard line. It went back a few yards and then went forward. So it went back about 2.5 and went forward about 8.5 or so. So that answer is very sensible. Okay, there you go. Parametric equations. Good luck.